to show you how to make a mechanical design and how to analyze the stress inside the component. So Alan, please share your screen.
Okay.
And are you going to model in SolidWorks or directly in ANSYS?
I can use in ANSYS.
Okay, so please show us ANSYS. So inside ANSYS, this is called the workbench. This is there is a traditional. Can you make it larger? How do we? How do you? I forget how to do it.
Okay.
No,
No.
no. Hold on, hold on. We are trying to see the full screen of your monitor. Full screen.
You see?
Change no over there. Change layout. I think. Change layout.
Okay.
Okay. Yes, spotlight. It's okay. And then you should be able to. Let me try it. What's this? This is remove. On pin. How about this? Okay, and then pin this one. Unpin this one. Okay. Oh, still very small. Picture. No, not this. Bring back. Full screen. Should be this guy. Yes. Okay. Good. Yeah. Go back to yes. Alan,
Yes.
you need to change the resolution of your computer. 解析度, make it lower.
Okay.
Change your resolution to a lower number. Yeah. Otherwise, the fonts are too small. Yeah, I think 12880. 12880.
0 and
960. Yes.
okay.
That's maybe lower. Even lower. Yeah. Because over here, maybe try 1024. Yes. Try this one. Okay, I think it's better. Now, I want to create a cylinder. 圆柱, create a cylinder.
Okay.
So over here, you can see on the left-hand side, we have so many module. Each module can operate a kind of finite element analysis. So he chose, what did you use?
And this one,
Static structure?
yes,
Yes.
static
So
structure.
he chose static structure. Okay. When you say static structure, that means it's not a dynamic problem. If you are working on a dynamic problem, then it's rigid dynamics. But he is only using static load. So inside the static, what did you do? Double click?
Yes, you can
Okay,
double click.
the
I have
module.
yes.
Okay, so he double click the module, then inside this area, this is like your working space. You can get rid of the second one. Yeah, so he put one module here. And if one day you need to work on multiple modules, for example, if you have if you have a liquid channel, liquid, and then you have liquid flowing. You don't need to do anything. I'm just explaining to them. Let's say you have a liquid channel and the liquid coming through, and inside, let's say you have a structure. Then you need to, if you want to analyze the liquid and also analyze the structure, they are two different kinds of physics. Okay, so this is solid mechanics. This is fluid dynamics. So over here for ANSYS, it has fluid dynamics right here. You can put that in the working space, and you can solve for solid and fluid separately, and then combine together. Okay. Can you operate this? Okay. So whenever, but today we are doing very simple things, just one kind of physics. But in the future, you can try to work on multiple physics. So usually, if you are working on multiple physics, for example, the deformation of solid requires information of the shear stress generated by the liquid. Then there are some interaction between at the interface of the solid and the liquid. ANSYS can handle this kind of simulation. Okay, but that's more advanced. We don't need to do that today. So, okay, Alan, what's next? Define geometry, right?
Yes.
So over here, you can you 往前一步? Hold on. So inside the geometry, make a click on the geometry. Yes, now click. Okay, and then, okay, show us how to do it.
And choose the design
New,
model.
okay, new design modeler. Okay,
Yes.
okay, do it. So this is not SolidWorks, not Pro E, not AutoCAD. This is the CAD design platform generated by ANSYS. It's not the best CAD designer, but it could be used. If you want to design your own geometry in SolidWorks, it's okay. You can complete your ANSYS or your SolidWorks or Pro E design, and then import into the module. Okay, so please create a cylinder for us.
Okay.
Do you need to draw a circle first?
Okay.
Yeah.
Here we can
Oh,
create
you can just choose. Okay, good. So primitives means simple geometries that is predefined by the computer. So cylinder is a primitive, and you can directly choose it. Okay, let's build a cylinder. Okay, can you build another one, a thinner one, next to this one?
Okay.
Yeah.
Then- then-
The radius, okay. Yeah, good. That's good. Can you make them longer?
Yes.
Okay. Yeah, that's fine. That's fine. Okay, uh, so yes, let's complete like this. And can you make the first cylinder longer? Is it easy to do it? Cylinder 1, okay.
Then
Change the length. Okay, 3 is good. Okay, good. So this is oh, okay. Do you need to add the material right now?
no, not in here.
Okay, so over here you create geometry. Very
Yes.
good. Do you go back to the module? Okay. Next, what you need to do is to choose the material, right?
Yes. We
Okay.
can edit the material in the engineer data.
Okay, so can you show us? Let's change to copper tone.
Okay.
So right now, by default, it was steel. Usually we work with steel. Can you choose? I think you can find copper somewhere. It should not be composite. Just try general material, and you scroll up. You should find copper alloy. Okay, let's use copper alloy.
And
So from ANSYS, you can already see a lot of non-material inside ANSYS. Okay, let's try copper alloy. Okay,
and
so how do you assign copper alloy?
and in here we need to go the model in
Okay,
here, then can assign it.
okay, show us. Alan, when you do everything, do it slowly.
Okay.
You are doing too fast because we cannot see you. We cannot see your mouse movement. Do
Okay.
it slowly, okay?
Okay.
So what do we do?
In here we can open the geometry,
Uh-huh.
and here is a solid.
Okay.
Then go down to the detail. Here is a material. We can choose it to change it.
To copper alloy. Okay, good.
Okay.
So from outside, you need to add the material you want to use in the library because ANSYS has so many materials to use. So from outside in the module, you can put what you can choose the material you want, and then inside this definition, you can then select the material you used. Okay, good. What's next? Do you create mesh right now?
No, not yet.
Okay. What's next?
Uh, we need to. We can choose the mesh in here now.
Okay. Yeah.
And
I think you can. Okay. So what is a mesh? Mesh is basically cutting this whole thing into small elements, just like what I showed you last time. And when we select mesh, usually there is a parameter that allow you to have bigger element or smaller element. So what is the property for mesh size? Can you show us? Sizing? Yeah,
um,
I think it's sizing.
sizing. And
Uh,
here can we can insert the sizing to set the size.
so what is the default? 预设, what is default?
Default is
Can you at the left lower? Yes.
over here.
So let me see. Uh, mesh. Oh, resolution is default. Resolution default.
Yes.
Can you try to change it? Resolution.
Default.
Yes. So right now the default number is 2. Can you use the default? Don't do anything and then general. Oh, we already have the mesh.
Yes.
So this kind is more like a triangular shape, but it's not triangle. It's I forgot the name. 四面体 what's a 四面体? Okay, basically if you cut inside, basically it's like our 粽子, right? Okay, so let's try to change the resolution to a greater number.
Uh,
Okay, and
maybe.
do you? I think you need to solve. So now you can see they become smaller. The element, can you change it to let's say 5,
Okay.
so we can see the difference and solve. Okay, then you from here you can see the element size becomes so small. Okay, So let's try to use 2 for now. Use 2. Okay. So by default, it was 2. Okay. Now, the next thing you need to do is to define boundary condition. Okay. Hold on. Let me tell them what is boundary condition. Okay. So remember on Monday we talked about a F vector, K matrix, and degree of freedom, right? Degree of freedom vector. So usually when you define a problem, for example, let's say we are going to fix this upper right corner to the wall, and we are going to apply a force right here. Fine, can Alan see this? No, right? Can you take a picture and show him this is what I'm going to do later on? And let me explain first. So if you do this, that means there is one node right here, right? So if our coordinate system is like this, if this is x, y, and z, then we have a force. For example, if this is node number 23, just for example, then for computers, it knows f node 23 along z direction, there is a negative force. And there's no other force on this node. So in that case, F23, X, F23, Y, they are both 0. Should be 0. Actually, it may not be 0. Because you only know this one. You're not sure if there's force along Y, X, and Y. How come you're not sure? Because there are internal forces. If I apply, this is external force. External force. Okay. If I apply external force, in between, inside the material, there are internal forces. So over here, some force will be applied to this node. These are internal forces. Okay. And we don't know how large those are. Finite element will solve it. So if we assign this boundary condition, we are sure one of the number, this one, f z23, we can only be sure about one of the number. Okay? And all the rest, we don't know. And when we assign boundary condition right here, like this one, we claim it's fixed on the wall. So for example, this is node number 12. In that case, because this is fixed, we are sure U12X, U12Y, U12Z, they are 0 because you say it's fixed. So in this case, there are 3 numbers here. They are U12X, U12Y, U12Z. They are all 0. So inside ANSYS, some information in the F vector will be known based on your formulation, based on your assignment. Some information will be known in the degree of freedom vector. So what ANSYS will do, ANSYS will try to solve for these 3 numbers, the corresponding 3 numbers. because if you have those three and you have three equations, you can solve for the three unknowns right here. Okay, and ANSYS will then try to solve for every other information later on. Basically, the software will try to solve for all the internal forces and all the degree of freedoms. Okay, so by solving this entire equality equation. Okay, so if you assign the boundary condition correctly, it should simulate what's going to happen. If you assign the boundary condition incorrectly, then ANSYS can still solve it. However, it will be wrong. So it's very important for you to assign the boundary condition correctly. Okay, you need to assign those exactly like the real world. Okay. Okay, so Ellen, did you already got my picture?
Yes.
So on the right edge of the entire cylinder, please fix them on the wall. Just
Okay.
fix boundary condition. Do it slowly.
Okay.
So I think it's called a fixed support.
Yes.
So apply fixed support, okay? Apply to the
And
right,
choose
right,
here.
yeah, right surface. Okay, and then say apply. Good. Now assign single force. But how do you do it?
I correct it. And here have the false.
Okay,
We can
but
choose it.
but this one applies a force on the surface, right?
Maybe I think I can choose in the
Surface
yes
only. So can you choose a point
point.
or component? Okay, okay. Can you apply to a point? Maybe from the on the left geometry, you need to select because you for computers it needs to know which point. You don't have a point.
Yes.
Okay, then just use the shear force. Apply to the surface. That's fine.
Okay. Yeah.
So it's okay. He's going to change the problem. Assign to yes. Is it on the surface or on the node?
On the surface.
So okay. So if you want to assign a force on the node, you need to let the computer find the node. But in his geometry, there's no point right there, no point object. So for easier demonstration, today he applied the force onto the entire surface. So in this case, this is a shear force, entire applied to the entire edge. Okay, so try to solve it.
And what force we need is it?
Oh, you mean what do we want to see? Okay,
Yes.
please show displacement, uh, uh, stress in every direction, and von Mises stress. Oh no, in the force, just going down,
Going down. Okay.
going down, going down. Yes. Okay, okay. Negative 100 Newton. Okay, good. So for the solution, can you turn on this deformation and say directional? Okay, and one more. Stress, say equivalent von Mises. Okay, and one more. stress again, and this time you can use maximum shear. Maximum shear. Yes, let's try to see this. One more. And stress. Let's see. Just I want to see stress along every direction. Oh, anyway, use maximum principle, the second one. Okay, maximum principle. Okay. Okay, let's solve it. Okay. So let's take a look at deformation. Okay, now from here you can make sure you check the unit. This is a millimeter, and this analysis basically, I think it shows you the maybe not even the nodal information. It shows you everywhere, and it will highlight the information by color. And over here, the maximum this deformation is 2.0 to the power of -6. So this is 2 times 10 to the -6 millimeter. So what is that? It's a 2/3 micron. So it's a 2 nanometer. So there is a 2 nanometer deformation right here. So very small. Is it? Is it nano? Yes, nano. Right. And what is the minimum? The minimum is uh, -2. So -2 nanometer. And it's right here. And this one is right here. The largest one is right here. So right at the close to the edge. But is it correct? Maybe not. So Ellen, let's try to uh, make our mesh smaller.
Okay.
That this time change it to 5. Okay. Solve
And
again. Okay. And let's check deformation again. So at the end, it's 1.9, 1.9, 1.93. Also nanometer. And pretty close position. Can we try even smaller? Let's
yes,
try 12. Oh no, 10. How about 10? Let's try 10. Okay, the maximum is 7. That's okay. Let's try the smallest. Yeah, the maximum is 7. Okay, and let's see deformation. Deformation. Okay. So okay, 1.94, and similar location. I think it's pretty good. Okay, let's take a look at stress, equivalent stress. It's too. I cannot. It's very hard to see. I think it's at the on the top. Is it? No.
over here.
Okay. It's very because it's in. I think it's close to inside of the material. Uh. Okay. So let's keep this number. We previously see 2 nanometer displacement, and the Van Mises stress is around uh 0.004 megapascal. Okay, so it's around 4 kilopascal. Okay, this is what we had. Okay, Ellen, can you go back to CAD design
Okay.
to our back to our geometry? Okay, let's do 倒角 around. So can you make around rounding? Uh, okay, please try to.
Like this.
But not there. 那个
Oh,
转角那边。
oh, okay.
So go back, go back.
Over here.
Yes, exactly. Yes. So yeah. Can you make it larger? Maybe 0.3. Okay. Generate. Okay. Now go back to analysis. And yeah, you can directly update and solve. Okay, directly solve. Do you need to remesh? It's okay. It will remesh, but it will remesh. Okay, good. And then let's see the formation. So max deformation now reduced to 1.8 nanometer. And okay, it reduced 1.8. And let's see principal the equivalent stress. Now is 9.5 kilopascal. So you can see if you have rounding, then your deformation reduced and the stress reduced. Okay, but is it accurate? Um, over here at the corner, usually you have stress concentration. So maybe it's accurate, maybe it's not. It's very difficult because for uh, even for research, sometimes we try to study stress concentration, and we know the software may not be accurate enough. Okay, so but you can use it as a reference. Okay. Okay. Good. Uh, let's make it more interesting. So Ellen, can you go back? Can you see the maximum shear on the left? 最大剪力. Let's see where is the. Okay, also same place. Okay, let's see maximum principle. Okay, go back to maximum shear again. So maximum shear, let me copy it. Tau max is 1.9 K Pascal. Yes, and that's the maximum principle. So this is a maximum principle. Should be okay. This is a 3.8 kilopascal, and this is von Mises. Okay, now we can take a look at every model we have learned. So we know maximum shear stress model tells us your largest shear needs to be smaller than your Young's modulus over your safety factor. Okay, and your safety factor will be, sorry, there's a uh, 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 divided by 2, right? Yes, two, for shear is divided by 2. So your safety factor would be 2 times this, okay? And this equals to around 3.8, okay? This will be your safety factor. And from here, you can tell very similar to over here, very similar to your maximum principal stress, because they are basically, they could be determined from the same Mohr circle. That's why the value right here and the value right here is very close. If you use normal stress, then your normal stress needs to be smaller than your Young's yield strength over safety factor. So at the end, you have same model. These two are the same. But how about von Mises? If we use von Mises, then it's a little different. Then we have 3.5. This is smaller, and we will see greater safety. How come? If we use von Mises, we have greater safety. Can someone tell me? Does anyone remember? If we use principal stress or shear stress, the number right here is 3.8. But when we use von Mises, the number here is 3.5. That means when we use von Mises, we have greater safety. Who remembers why? Anyone? It's in our second part of our exam. Remember? More aggressive. More aggressive. Yes. Yes. Remember, there's a when we work on the model, there's a model like this. Thank you for your answer. This is our maximum shear stress model. And this is for plane stress problem. This is the stress in the first direction and second direction. And for maximum shear, we have this this shape. And for maximum the other model is maximum distortion energy model. And this one is based on von Mises stress. And when we introduced this model, we said maximum shear is more conservative. And on the other hand, the maximum distortion energy is more aggressive. Okay. So that's why if we use von Mises stress, the estimation of your safety is higher. You are not conservative. Okay, so please try to combine what you learn with what you work on in the future. And you need to make your own decision. Do you believe in von Mises stress, or do you believe in shear stress? If you are conservative, you need to use shear stress to estimate your safety, because your safety is lower. So if you one day in the future in a company, your supervisor asks you to design something and you need to know your safety, then you need to question yourself or question your colleague. Do you want to be more conservative or less conservative? Remember, different models indicate different results. When you use von Mises stress, you are more aggressive, less conservative. Okay, always remember that. Okay, Ellen, let's try something fun. Let's go to our model. Go back to the model. Can you 挖一个洞 Can you make a cut vertically？垂直从上面挖个洞，随便挖。So it's a extrusion of cylinder but cut，应该是挤出 cylinder，然后但是是用挖的，可以吗？Oh, you need to make a drawing. Okay, okay. I think he's nervous. He doesn't say anything. Don't be nervous. Okay. Are you nervous?
No, it's okay.
Okay. Yeah, just okay. Draw a circle. Yes. Somewhere. Okay, that's fine. Can you make it larger? Okay, so he draw a circle on this plane, a little larger. That's okay. I think that's fine. If you uh, okay, make it 0.7. 0.7 point. Yes, yes. Yes, I think that's nice. And make a cut.
Okay.
So Ellen continue. 我解释一下. So let's try to cut away this material, make a through cut from top to bottom. Continue, you can continue.
Okay.
Yeah, I just talk to my students. So if we make a cut, a through hole, this structure will become weak, but of course become lighter. We will observe what's the deformation and what's the stress. How does it look like later on? Okay. Did you? Okay, good. He already cut through this structure. This structure can be seen everywhere. Then you realize you will realize a structure like this will be weakened a lot. Okay, let's go back to analysis. Let's solve everything by same parameters. And let's now take a look at deformation. So where is large maximum deformation? Okay, it's right here. So the place that has larger maximum deformation changed. It's not at the original place. It changed to here because this structure becomes so weak. And let's see how large. So this is 1.64. So basically, basically 16.4 to the 10 to the times 10 to the power of negative 6. So this would be 16.4 nanometer. So originally, the maximum deformation was 2 nanometer. Now it becomes 8 times larger because you drill a hole. Okay, let's take a look at stress. Okay, equivalent stress. So the corner has the largest stress. And then we can see it's 0.01 megapascal. So it's 10 k pascal. It was 3.5. It was 3.5. Now the stress become 10, 3 times larger. 3 times larger stress at the corner. And also the location changed. Alan, can you 看一下刚刚的位置? So previously, I think it's over here. This location was the place where we have the largest stress. So 这个是可以分析，是不是？分析点吗？
这里走选区，我
It's okay. It's okay. We can check the color actually. So if you check this area, this is where we have largest stress, and the stress level is around this region. So it's around between 2 to 3 kPa. So similar to what we had earlier. It didn't change much for this area, or it could be even smaller stress, because right here it becomes so weak. All the shear force generated here is trying to create bending at this position. Okay, and over here, the original place, the stress become maybe a little bit lower. Okay. So Ellen, are you able to do fluid dynamics easily? Is it easy?
No.
It's not easy. Okay.
Okay.
I mean, if we create a very simple fluid domain,
Maybe I can try it.
yeah, that's a separate problem. It should be easy.
Okay.
Okay, so let me show you if we want to a fluid problem. Okay, so yeah, ANSYS, thank you. You can turn this off. Okay, and you can close the structural module. You can delete module A. Okay, yeah, you can delete. I will tell you what to do.
Okay.
So now let's try. Hold on. Try fluent. The second one. Yeah. Try fluent. Okay. So how come there are many different kinds of fluid flow? CFX, fluent, poly flow. What does that mean? ANSYS is a huge company. Fluent was a smaller company. But Fluent, when I was a PhD student, I used Fluent. I didn't use ANSYS for my PhD. When I graduate, ANSYS purchased Fluent. So Fluent become a part of ANSYS. And you can already use Fluent inside ANSYS. Okay. So now, Ellen, please try to create geometry. So if you want to model liquid, what you need to design is the area of your liquid. So Ellen, can you design exactly same thing? 就是两个圆柱一模一样 exactly same. So what we are doing right now, we are just like modeling a pipe, the area inside the pipe. Okay, so right now what Alan is doing, he is modeling the empty area inside the pipe, 管子内部. Okay. Okay, that's good. So let's imagine this is what's inside the pipe. This is where your liquid is. Okay, now you can go out. You can go back. And the most important thing is boundary condition. Let's go to your model setup. I think in setup.
Okay.
Okay. Now for the most important thing is boundary condition. But let's see what is the material. 这什么材料? What is it? Is it air? Let's see.
We did not define it yet.
Okay, so change to fluid. Change to fluid. Yes. So now this whole thing become fluid. And go to material, see what is that? Material. Oh, only here. Okay.
Okay. Outside.
Okay, let's assign a new material. Let's change to water. Can you
We need to insert
Okay.
it in outside.
Okay, let's go outside and then pick up water.
Water.
Can you are you able to就像你选那个材料清单那样子
这个功能没，我不知道为什么它没有在里面。
？Okay, try new material. New material. Please, hold on. Refresh model cell in the project after creating new. Say okay. Okay. Just say okay. Okay. Okay, never mind. Just don't do anything. Just let it be liquid. Okay, now can we try maybe mesh? What do we do? Let's generate. How do we 怎么建边界条件 boundary conditions?
好像，那个是在下面的
Okay, okay.
layout 那边。
Okay, okay. Let's try to do boundary condition.
OK，OK，
Okay, this is fine. Okay, let's try setup. Okay, hold on. Okay, 3D problem, good. Just start. Just by default. Okay, this is something new. I have never seen this. Okay. Okay. The resolution is difficult for us to read. 解析度都太难。materials 左边 left fluid. Okay. Okay. I think the resolution is too small. 那个解析度太差了，所以
东西挤在一起。
I mean, change resolution first. Okay, this is a new interface. I have never seen this before. 你调一下解析度啊，电脑。
好，我等调
1 to 80. But eating. Okay, try this. Okay.
Maybe I close this first.
Okay. The most important thing should be set up. 现在就定边界条件就可以解了。Okay, general. Okay, just say okay. Okay, good, good, good. So boundary left, boundary conditions. 左边 boundary conditions. Yes. Boundary, B. Boundary.
On the here.
Oh, yeah. Say 你选这个 wall，第二个 wall。OK, wall solid. OK，第二个，okay, let me see. OK，just say OK。OK. You need to pick up. Let me see. 你在左边有一个 wall，里面有一个 wall，看一下。OK，wall solid 好。它已经是 wall solid。OK，不要管它了，那就是we need to find inlet. inlet. Oh, mesh interface. 再下一个 mesh interface. Mesh interface. Yes, yes, yes. 答案什么？Auto create. Try auto create. Two zones between boundary. From boundary zones. 哦，麻烦了。Okay, turn off, turn off. Okay, I think this is going to take too much time. I didn't ask him to try this before. It's okay. Then let me. Can you? Maybe we just go to internet and look for one solution. That's faster. Go to internet
Okay.
and say CFD result. CFD and say result. RESU and result. ULT. Yeah. 对，第二个。Okay, and then find pictures. 图片 just 图片 Yeah. Okay. Scroll down. 往下。Let me find something similar. Scroll down. Continue. Maybe 继续。Okay. 左下角这个。Okay. So this is I think this is like a fan, and it's simulating what's inside the fan, and you model the fluid domain. Sorry, this usually a simulation like this takes a lot of time to set up, and I didn't tell my student to prepare this, so it will be take too much time for him to get ready. But usually, what happens is if you have a fluid domain, for example, like this, you need to tell the computer the boundary conditions. For example, this could be a inlet, and this could be outlet, and this could be the wall. And you need to specify what's inside the material, inside the pipe. You can say, okay, this is water. Okay, so then for the inlet, you need to specify what is the volume per unit time to represent the speed of the fluid. And then you need to cut this whole thing into mesh. And usually for fluid, it's very complicated. You need to specify the wall conditions, such as, do you have boundary layers? Have you already learned fluidics? Fluidics. You guys learn fluidics, right? 流体力学. No. The course. Yeah, fluid mechanics. So you must have learned something called boundary layers, right? Do you remember this figure? You guys remember this, right? Fluid dynamics. Nobody replied to me. This is inside the boundary layer. So the velocity over here, the velocity is 0. And this is like the velocity of the stream. This is velocity of the stream. And inside the boundary layer, the velocity changes from u goes down to 0. Okay, and if you want to simulate a fluid domain, the software needs to simulate something like this. The velocity close to the wall is almost 0. and the velocity at the middle is the highest. Okay, and at the end you can see, Helen, 你这个右边这个图下面有一个那个流线图 ，yeah, yeah, this one, yes. So you can see the streamlines, the streamlines. OK 啊，Alan，你有没有我那个心智图那个网站 task？no，对 task，去那个 task 没有。哦，我贴给你。Hold on。
好，
Fine, do you have it? The web page for the mind map. Yeah. I want to show the students some of my previous results. Sent to Ellen. Do you have it? Hold on.你问一下实验室谁有那个网址啊？
好，问一下。
Okay. I have it. Hold on. Let me paste. Okay, go to the link. And go to, let me see. 右上角 fluidics, upper right fluidics. And go up. Fluidics, yes. And then turn on 那个第三个 the third one, console 2011 from the top console 第三个 COMO 那超链接点一下。Okay, scroll down to find the pictures. Okay, so this is a heat sink 水冷散热 heat sink using water to cool down CPU. When I was a master student, we designed this to cool down CPU. So in Fluent, actually we use another software. We model the liquid domain inside. So water comes from the top and then goes out from the side. Okay, 往下 go down. So this is how we define the boundary conditions. Okay, go down. Okay, stop here. So you can see this is called streamline 流线. So from the inlet, the liquid comes down, and you see a lot of vortex right here, and then goes up from the outlet. Okay, and from here you can tell this is temperature distribution. The purpose of this is to cool down the CPU. So the heat, this is at the center, the CPU is right here. The heat is being taken away to the side and then goes out. That's why the entire heat sink is cold, it's not hot. 这是一个水冷散热 liquid comes in at the center and take out the heat. Okay, continue, go down. I think we have several different designs. Go down. Okay, no more. Go back to my map. My map. Okay, let me find an interesting one. Let me see. Hold on. OK，有一个 ERAC 2015，ERAC 上来一点，滑鼠上，再往上，ERAC，耶，这个是左边，
这个
，this one，go down，go down， continue，继续。他说 OK，we truly made the heatsink。OK，go down，go down，往下。OK，go down up。So we even make this by 3D printing because we know when the liquid goes in and come out, the heat will be taken away. This heat sink is cold, it's not hot. So it could be made by plastic. Okay, continue to go down. Okay. More. Okay. Even more. There's no more. Okay, boring paper. Okay. 换一个。This one is too boring. OK， 上面那个 FEF， 看看 maybe more interesting. OK， 往下。Yeah, this is done by the final element. Okay, go down. Okay, we try different shapes inside the channel. So when you work on your project, you can try different geometry. Use final element to see the results. So just like what we did. Okay, but at the end, it doesn't. The result tell us the cooling efficiency didn't change much. OK， 换一篇。OK， 那个右上角有一个 Aries， 往下2015，往下一点，再往下一点。对，这个。Let me maybe more interesting. Go down. 一直往下。Go. Okay, very boring paper. Okay， 换一个。So let me see which. There's one is very interesting. I try to find that one. Where is it? 有个绿色的 TW 2015。Yeah. Try this one. Go down. 没有图片。Okay, there's no picture. Sorry, I couldn't find it. But anyway, so in the past, finite element truly help us to simulate the performance of a device. So in your project, no matter what you're working on, you can start to make design. You can change your design and see if you can make it better. And I can teach you what you can do. Because later on, when you try to improve, Alan， 那我们今天就这样子，感谢你。Can we
好的，谢谢老师。
say thanks to Alan? Thank you. Let's clap our hands. Alan，谢谢 ，Thank you.
谢谢老师。
Okay, bye bye.
老
So
师，拜拜。
I want to talk more to you, tell you more about your project and what you can do later on. So now, let's say you have a initial design.